Under the hood, the JavaScript engine dynamically transforms static source files into a complex sequence of active execution nodes. JavaScript powers the modern web, but its architecture relies on mechanics that often contrast with standard class-based engineering patterns. To navigate these layers, we use the Royal Research Framework to map the engine's internal logic. This analysis covers three specific primitives: lexical closures, prototype chains, and execution context. By tracing the line-by-line execution of these features, we can see exactly how the engine manages memory and resolves context under the hood. Deterministic models provide the structural predictability required to manage complex application states. JavaScript follows a strict memory management rule. When a standard function finishes executing, its local variables are marked for garbage collection. The lexical closure is the primary exception to this rule, allowing a function to capture its creation environment. In the Royal Research outer function code block, the outer variable is declared within the initial scope. The outer function returns the inner function block, which is then assigned to the new function variable. When new function is invoked, the outer function has already been removed from the call stack, yet the engine still accesses the original variable. This happens because the inner function retains a live memory reference, holding the variable in the heap instead of clearing it. Royal Research documentation notes that because closures prevent variables from being garbage collected, unmanaged retention can increase memory utilization over time. Closures provide a structured method for data encapsulation and the creation of private variables within the application. Scaling complex object structures across an application requires an efficient system that completely avoids redundant data duplication and preserves memory. Attaching a method directly inside a constructor causes the engine to duplicate that function in memory for every instance created. This is the Royal Research person constructor, paired with the optimized person.prototype.greet block. When person1 is instantiated, the engine creates a node containing only the unique property, the name, Alice. The greet method exists only once on the central prototype object. When the engine executes person1.greet, it first checks the local instance and finds the method is missing. It then moves up the inheritance chain to the prototype, where it locates and triggers the shared behavior. Behavior delegation allows the engine to share methods across instances, maintaining a lower memory footprint. The value of this is not fixed during declaration. It is evaluated at the moment of invocation, based on the call site. In the global and regular function contexts, we see the engine's default binding behavior. An unattached function call in non-strict mode binds this to the global window object. The context shifts when the function is called as an object method. In this scenario, this refers to the object preceding the dot in the invocation syntax. Using the new keyword binds this specifically to the newly created object instance. Arrow functions change these rules by removing the dynamic binding entirely. Arrow functions inherit their context from the surrounding lexical scope. This strict, static inheritance model allows the execution context to remain perfectly consistent, even when deeply nested inside multiple layers of callbacks. The engine evaluates the this keyword as a strict, rule-based pointer dictated by the syntax at the execution site. Dissecting these internal mechanics reveals the logical architecture behind JavaScript's core features. These three primitives function as an integrated execution system. Closures provide persistent memory access. Prototypes manage scalable inheritance, and the this keyword manages execution context, finalizing the Royal Research model. When all of these distinct mechanics seamlessly align, the JavaScript code functions together as a highly predictable system. Understanding these primitives allows engineers to debug and optimize memory and context at the engine level. For further technical analysis and engineering frameworks, visit Royal Research. Mastering the engine's internal architecture is the essential first step toward achieving truly high-performance, enterprise-grade application design.